The subject of nuclear astrophysics, the overlap area of nuclear physics and astrophysics, is of great significance now in physics research today. It answers some of the key questions like the stellar structure, like the production of elements in stars, and the death of large stars. Particularly of interest today are some of the experiments done in the laboratory all over the world which are assisting in this research on nuclear astrophysics. We are very happy that one of the renowned nuclear astrophysicists of the world, Professor Klaus Roves of the University of Bochum, is here with us. And we'll discuss some of the key issues of the area of nuclear astrophysics. I should also mention that Professor Roves recently was the recipient of the American Physical Society's prestigious Hans A. Bethe Prize for the year 2010, given by the Division of Astrophysics of APS. Now, Professor Roves, what do you think is the importance of nuclear astrophysics today?
Well, we learned over the 50 past years that we are connected to distant space and time not only by our imagination but by a common cosmic heritage, namely the chemical elements which make up our bodies and our surroundings. These chemical elements have been produced over billions of years in very massive stars, and these stars, when they had exhausted their energy reservoir, they exploded. And as a consequence of this explosion, they ejected the treasures they made during their lifetime inside their stomach out into space, where these elements mixed with the ashes and dust of other star explosions. Therefore, the elements in interstellar space, out of which our solar system and therefore the Earth was born some 5 billion years ago, inherited the ashes of previous stars. So the oxygen and nitrogen in our air, the iron in our blood, the calcium in our bones, all these elements were made inside stars many billion years ago. In a certain sense, therefore, we all have been inside a star, we all have been between the stars, and since the universe has a beginning with a Big Bang, we all were once there. This beautiful picture of the universe and its evolution, the origin of the elements we are made of, this beautiful picture needs verification, justification by experiments. Astronomy is a field observing the universe, but to explain the observations of astronomy, one needs astrophysics. One needs to study the microscopic processes taking place inside the stars, and only when one has done these experiments, then with that information one can see whether one can understand the observed features. Of course, these experiments are extremely difficult. Einstein said once, "The Lord is tricky, but he is not mad. He allows you to find his secrets." But these secrets are not easy to find, and you must spend a lot of thinking and a lot of imagination to untackle these secrets. And that's where the open field is we have many beautiful theories, but theories are not truths. Every theory must be confronted with experimental facts. And only when we have the facts, then we can slowly say that we understand the universe and its objects. And I'm very glad to be here and having contact with many young Indian students, which have made a very great impression on me, that with their excitement, with their intelligence, they will be able to contribute a mosaic stone in this beautiful picture of the universe and its objects.
Would you mention some specific experiments done in the laboratory in the last few years which really helped some of the key issues?
Yes. There was a very important issue how the sun, our sun, produces its energy since 5 billion years. And only through the development of nuclear physics in the 1930s, one found an answer, namely that the sun produces energy by nuclear power, by the fusion of hydrogen, which the sun has a lot of, into helium. With that assumption, one could understand the solar luminosity, one could understand the long burning time of the sun. But as we learned in physics, a hypothesis that the sun burns nuclear has to be proven. Once, in the Middle Age, people thought the Earth is a flat disk, because when you look at the horizon, you see a straight line, until improved observations showed that the Earth is not flat, but a sphere. Therefore, what we think from normal human mind understanding must not necessarily be truth. Therefore, the question was, can we somehow look inside the sun to see what the sun is doing right now? Whether the sun really burns fusion reactions to make energy. And in the 1960s, the idea was that there are some strange particles created in that fusion called neutrinos, little neutral particles. They have no mass or very little mass. They have no charge. They have plenty of no properties, and therefore they can escape easily the sun and arrive 8 minutes later on Earth. And so if one could observe those neutrinos, one could look inside the sun as it was 8 minutes ago. That means practically today. And indeed, huge detectors have been built, and one found neutrinos. So it was a great success, because this hypothesis that the sun burns on nuclear power appeared to be proven. However, there was a red hair in the soup, because one did not observe the full amount of neutrinos as expected, roughly a factor 3 less. This could mean on one side that now the sun produces less energy, and therefore the sun will shine a factor 3 less powerful. Now, of course, it takes a while until the sun will shine less, but even a little bit reduction of solar power would produce an ice time on Earth, a deadly consequence for human beings. So one hoped for another solution. One possible solution was that the microscopic processes inside the sun that were based on experimental data but not measured directly at the energy relevant for the sun, that they could be wrong. And for that reason, I, together with an Italian friend, Gianni Fiorentini, some 20 years ago, we decided to have a laboratory underground in the Gran Sasso mountain, about 2,000 meters below the top of the mountain, and there we could perform such experiments for the first time. The laboratory is called Luna. Luna is the Italian name for the moon, but in this case it doesn't mean the moon. It stands shortening for Laboratory Underground for Nuclear Astrophysics. And for the first time we could measure directly these reactions inside the sun at the relevant energy and could show that the previous extrapolation was correct. Therefore, the solar neutrino problem, this factor missing, factor 3, could not be based on nuclear physics. The reason why one is behind this factor 3 is the following. The sun is a test case for astrophysics. The sun is the best of all studied stars. And if we don't understand the best studied of all stars, we have no hope to understand all the other billions of stars. Therefore, one had to understand very well the sun. And that's why for about 50 years, many scientists were involved, including nuclear physicists. And as I said, this was a key that the solar neutrino problem could not be solved by nuclear physics. And only a few years ago, one found the answer by another neutrino detector called SNO in northern Canada, showing that neutrinos can oscillate, a complete new property in nature. And so I think nuclear physics and these experiments took about 6 years of running. So these are not experiments for a weekend. It takes lots of bones, lots of strength, and again, only because there were many young students involved which have power, which have fantasy, we have energy, enthusiasm, you can do such experiments, and I'm sure you have the same quality of students here in India to attack many of the remaining key issues in the universe.
Okay, what are the interesting future experiments and theoretical challenges in nuclear astrophysics that you think of?
Well, I think most of the so-called key reactions in astrophysics in stars operate about many thousands of reactions, but only about 20 of them are of key importance, because they also determine how a given star evolves in the future. Whether he explodes or does not explode, nuclear physics is the key which will give us the answer. So amongst these are reactions in the hydrogen burning, like in the sun, then there's helium burning, and most important for the final evolution is what is called carbon burning, and there we have no information how this burning appears at the relevant energy. And indeed, the explosions of stars called supernovae, we see them every night in some galaxies. In our own Milky Way, the last supernova was 400 years ago. So every 300, 400 years ago, we expect another supernova in our Milky Way. So right now, any night there could be another supernova. And the supernova will be so bright, it will be another full moon on the sky. But theoreticians have not managed to simulate such a star explosion on their computer. They have lots of problems, and if we would not see supernovae every night. The theoreticians would say supernovae cannot exist in nature because we cannot simulate it on our computer. I think a major piece of physics is missing, and I'm convinced that nuclear physics might be part of it. So fusion of heavy ions, carbon plus carbon, is very important to understand, for example, the explosion mechanism in supernovae.
Now let us come to the question of funding. How do you think nuclear astrophysics is funded in Europe, in the different countries?
Well, I think not well enough. Nuclear astrophysics was for many years dominated by one lab, namely in California, at Pasadena. It's the California Institute of Technology, and there it's a so-called Kellogg laboratory, where famous physicists like the Nobel laureate Willy Fowler worked, and he dominated essentially for decades the field. When he died, and also I was there and I fell in love with the field, and when I turned back to Germany I continued this research field, but it was considered as something exotic. It was not real nuclear physics, and nuclear physicists dominated the funding, and the astrophysics got a little breadcrumbs from the table. Not enough to live and too much to die. So we never got really well funding. Now slowly it changes because the nuclear physicists themselves found out that their future lies more in astrophysics. But they still only support themselves, namely what they now have available, radioactive ion beams. While the classical fields, like as I said, these key reactions, nuclear physicists think, oh, it's all well known. It's old kind of physics. No, it is a physics which we need to understand if we want to learn how the universe works. So we are still not treated well, although we give a justification why nuclear physics should go on. But we are not treated well. We are not given enough bread and butter to do our experiments in the way they should be done. So I must say my answer is no. Although nuclear astrophysics is at the frontier, it is a very important field. Our nuclear physics colleagues do not take us with a weighting factor to continue this research with funding, so we could go at a better speed. We have less funding, so therefore things take longer. We have to develop ourselves equipment with students, which takes long time. Of course, I like that students themselves get hands on equipment. They learn that way much more than if you buy something from the shelf. They build something and they have the tears if it is not successful, and they have the joy if it is successful. So I think that way they get hands on nature and learn what to do, and I think that's an important aspect for education of young students.
Yeah, at this point I should mention that India also is planning to have facilities. There is this concept of India-based Neutrino Observatory, or INO, where the work will start very soon of developing the underground laboratory in Tamil Nadu, and so maybe 5-6 years from now one can start doing the first experiment there. This will be one of the first Indian underground facilities. Along with that, in nuclear astrophysics, Saha Institute of Nuclear Physics in Calcutta is planning to have a facility for nuclear astrophysics. It's called FRENA, Facility for Research in Experimental Nuclear Astrophysics. So India also has recognized the importance of the areas of neutrino astrophysics and nuclear astrophysics, and there is a fair amount of funding coming for this. Now, Professor Robs, this is your second visit to India, and how do you enjoy your stay here?
Tremendously. I like the people, I like their friendlyship, I like their hospitality, and I enjoy nature. I enjoy this rich garden of Eden, the kind of paradise you have here. And this is my second visit, and this time I could stay a little bit longer than on my first visit, and I enjoy it tremendously. And if the Lord gives me a little bit more years to live, then I will be very pleased to come back and be part of your enterprises. I'm sure you will be successful because you have very intelligent, eager, young persons to attack the impossible. I call all these experiments impossible. But there's nothing impossible in life if you have young people. Young people are optimists, and you need to be an optimist in order to be a realist. A pessimist would always say, oh, it will not work, so he will not even start doing it. You must be optimist, and I think your young people I met now in Calcutta and met here at the school, I see them in their eyes optimism, and that's the key fire for success.
So Professor Robs loves communicating and loves interacting with the students. In both his visits we have seen that. So what is your last message for the students in India who are pursuing nuclear astrophysics and nuclear physics?
Have courage. Never give up on problems. Always problems have a solution. And sometimes even if you work on a problem, you find something surprising, which then even leads to another field of physics, some applications, which you would never find such a new development from a pure theoretical ground. Only when you try to do experiments, try to solve problems, then you will sometimes be confronted with something nobody understands. And that, as I said, might lead to new developments, even industrial. And so my message is to the young Indian students, have courage, hang in there, you will find a solution, maybe not tomorrow. Sometimes one has to work 2-3 years on a given problem, but it's worthwhile to find out the secrets of the Lord, or of Muhammad, or of Buddha, whatever Lord you believe in.
Thank you very much, and thank you for coming to India. I am sure you will make more visits, and we will really welcome that.
Thank you.